So welcome everyone. I'm really happy to have the opportunity to introduce Professor Barry Mazur. So Professor Barry Mazur obtained his PhD from Princeton University in 1959 and then spent a year at the IS and then moved to Harvard, and that's where he is today. So he is the Gerhard Gada University Professor of Mathematics at Harvard. And well, Professor Mazur has so many prizes that it's really hard for me to give a full list here, but just let me mention some. The Veblen Prize, the Cole Prize, Steele Prize, member of the National Academy of Science, several honorary degrees from different universities, and in 2011 he got the National Medal of Science. So Professor Mazur is not just an outstanding mathematician, he has wide interest in many branches of knowledge, and he has influenced many of his colleagues at Harvard University and worldwide. In mathematics, his contributions go beyond number theory, but let me just mention what I can talk about, which is number theory. So in number theory, Professor Mazur basically shaped what is arithmetic geometry today. His contributions are just deeply valuable in the community. So his paper on the Einstein ideal, for instance, is the foundation of the modern theory of modular forms. His contributions on Iwasawa theory, both in the analytic and algebraic aspects, are what people use today as a standard for studying this subject. His contributions on the theory of deformations of Galois representations are exactly what was needed to go ahead and prove Fermat's theorem. So it's hard for me to tell here how important are the contributions of Professor Mazur, but I think that something I can tell you is that it's not just in mathematics from the technical point of view, it's also at a human point of view. Professor Mazur is known as a really generous person when it comes to sharing his knowledge. He's always open for discussion, to give feedback, and it doesn't matter how boring is whatever you're going to tell him, he's always going to be interested and will tell you something smart about it. So, with no further delay, let me just give the microphone to Professor Mazur, because I'm sure we're all waiting to see what he has to say. Thank you.
Yikes, Hector. Wow. I don't know whether I deserve all that, but I'm more than happy to talk about the arithmetic of curves in the context of the Einstein public lecture this evening. Here's the eponymous Einstein there. With a quote that suggests that we're going to have a sort of an easy time of it in the mathematics that I'm going to talk about this, this hour. But what I'm going to do specifically is talk about ways of understanding algebraic curves and their arithmetic properties. More specifically, I want to talk about rational points and the interplay between arithmetic and algebra. And that has fascinated mathematicians from Diophantus to the present. I want to give a survey of current approaches and conjectures in this fast-moving but also ancient subject. We're going to talk about curves, so I better throw a curve on the screen. And I want to remind everyone that this is a plain cubic curve described by a single equation in two variables, x and y, of degree 3. And no matter how you describe a curve, it never comes to you in a floppy way. It always comes with more structure than you can imagine, depending very often on the description. In this case, for cubic curves, as you can see by the two red points, P and Q, if you draw a line between, a straight line, there's a unique straight line between those 2 points, because the curve is cubic, it'll intersect in a third point. And if the first 2 points are rational, and if the curve equations is rational, then the line of the equation then the equation of the line through P and Q is also rational. And so therefore the third point, R, that is picked out by that intersection is also rational. This is an amazing structure which leads to a group theoretic description of these cubic curves. But I want to start with a sort of a more general query. I don't want to call it a question that would honor it too much. Suppose you have 3 different and possibly even incomparable ways of proving that a certain set is finite. And you find yourself wondering, why is that set finite? You then have 3 different incomparable answers to that question, and the natural query is, is there some way to unify these 3 different answers to the question? I say this because first this thought might arise later in this lecture, and the line at the bottom, the red line at the bottom, is in a situation where at present I can't imagine any roads to such unification, except there may be hints. And if there's any theme that one can express in this lecture in one sentence, this is the thing that animates me at the moment. It's not my work, by the way. It animates me because I love it. Now, mathematics aims to explain and often asks what I want to call what questions and how questions. That's, so Aristotle organized this retinue of possible formats of questions. We might wonder what is the constitution of something, what is the truth of something, what properties does something have, how do we construct something, how do we compare something to something else. These are the standard ways of formulating a question in mathematics. But lurking behind sort of any of these questions is some, as I have on the screen there, perhaps ridiculously naive wondering sort of question that may not have any serious answer. Why is X true? So, as I say, it's amusing and somewhat baffling if you have 3 different incommensurate explanations of the same phenomenon. I'm going to start with ancient Greek mathematics, or at least an allusion to a beautiful piece of ancient Greek mathematics about square roots. In the text of Diophantus, he will refer to a square root. He wouldn't use that language. He would call it a side, because it's sort of essentially always in the background of much of Diophantus is hints of geometry. So a square root would be a side. One might assume a side of a square, and one wants to know the square root of the area of that square. So here's the problem that I want to start with. Find 3 squares, which, when added, give a square, and such that the first one is the side, that is the square root of the second, and the second is the side of the third. Now, Diophantus would be asking the question sort of in the diction of the blue line at the top of the slide. You have three squares, x squared, which is the side of x to the fourth. He wouldn't use those terms, of course, which is the side of x to the eighth, and you want that sum to be a square, and we can simply simplify it by dividing by x squared, ending and switching left and right of the equation, and ending with this sextic equation, y squared equals x to the sixth plus x squared plus 1. Now he offers a solution. X equals a half. You can try it. There it is. 1/2 squared plus 1/2 to the fourth plus 1/2 to the eighth is 9/16 squared. But he also gives a hint about how he arrived at it. He noticed that the square of any number, a plus a half, is a squared plus a plus a half squared. So if you take a to be 1/2 to the fourth, you win. You get 1/2 to the fourth squared, which is 1/2 to the eighth, plus 1/2 to the fourth, plus 1/2 squared, is that number that you started with squared. Of course, what Diophantine won was a single solution. And what Diophantus won was a single solution. And if you look through his list of problems, you realize that he's not keen on quantifying. So you don't know whether he's wondering what are all solutions of something. But anyway, he found this single solution. But we, of course, wouldn't stop there. We want to find all solutions of such problems. And I put it this way: find all solutions of the above problem in positive rational numbers. Okay. That problem was solved a mere 17 centuries later. A Diophantus solution is the only solution in positive rational numbers. He was pretty lucky in some sense. That is, as we would put it, the only positive x-coordinate of a rational point on the curve that is given in the displayed equation is x equals a half. And this is by a thesis, a Berkeley thesis of 1998, I think. It's actually quite beautifully written thing. You can just click on his name on the web and you'll get it. We're going to come back to this a bit more later. But I just want to mention that such cross-century conversations, so to speak, between Diophantus and Wetherell can be fruitful and coherent in mathematics, and it attests to some stability regarding our subject, our common language, modes of expression, modes of operation. And that's a kind of a blessing in a way. You might ask, why would you ever want to study rational points on curves? And I have a friend who always makes the distinction between agriculture and horticulture. Agriculture is geared to the practical, that is to say, actually producing food. And horticulture moves to the beautiful, that is to say, gardens, flowers. I feel that the study of rational points contributes to both agriculture and horticulture for mathematics. And as for being practical, maybe we want to spend a moment thinking about this. Sometimes an algebraic curve presents itself as a sort of museum for some specific genre of mathematical object, so that every point on that curve represents a particular mathematical object of that genre. And as it moves from point to point on the curve, one samples all the different members of that genre, and even better, there's a kind of geometry there that is, say, if the 2 points are close, the members are sort of close in properties and predicates of various sorts. So here's my example. This is called moduli. My museum of mathematical objects are those squiggly things, parameterized by some rational points on some algebraic curve. And if the point on the curve is rational over some field, say the rational is Q, the corresponding mathematical object would be defined over that field. And such a curve, or higher dimensional versions of this, is then said to represent the modular curve or a variety of moduli for their genre. To find all the mathematical objects of that genre that can be defined over a given field K, you're led to the problem of finding all K rational points on the corresponding modular curve. You might say that this is a really nice practical reason for studying rational points on curves. One might almost also say that that's the only reason, in that given any such situation, you might try to doctor it so that it does exactly that. Anyway, it's a basic tool for determining and classifying objects of interest. So let's begin with the Greeks again, Pythagoras. I'm considering the projective plane curve that everybody knows. I'm thinking of it with homogeneous coordinates and projective space, so I'm thinking of these projective points. And you might think of that projective curve as the moduli space of similarity classes of right-angled triangles. Let us say you give me such a point, you'll produce a right-angled triangle thanks to the Pythagorean theorem. And conversely, so that blue throwaway line acknowledges both the Pythagorean theorem and that you can express Pythagoras' theorem in a funny way as a moduli problem. You can do it in other ways too. You can say triples of positive integers, a, b, c, such that a squared plus b squared equals c squared, is in one-to-one correspondence with right-angled triangles. So that's also kind of moduli, a museum of right-angled triangles, or rational solutions as well. And in the rational solution situation, there's even a rational parameterization in a one-to-one way of those solutions. And that's affected by what used to be called, I hope it's still called, the sweeping method, where you consider a fan of straight lines with rational coordinates that meet the curve at one rational point. And since the curve is a conic, is degree 2, it has to meet the curve exactly at one other point, and that one other point is therefore also rational. So that's the sweeping method. You make a fan of lines through a given rational point. You have to start with a rational point on a conic for this, but in the case of the equation I gave, there is. Moving a millennium up from Pythagoras, we have the congruent number problem. It's also a moduli problem. We can keep to right-angled triangles, but fix the area of such a triangle. So in terms of the ABC, the sides of the triangle, the area would be AB over 2. And you might consider the moduli problem of the family, if you wish, of right-angled triangles with that fixed area. And this is a theme that has been sort of fairly, if not continual from the 10th century to the present. You can make new parameters, and I don't expect you to sort of note this on the fly, but if you call x and y the displayed expression in terms of the area and the sides of the triangles. And if you note that with a little bit of arithmetic, or algebra if you want, you can get the three sides, A, B, C, back from knowledge of x and y and the area. And the way you do it is in the essentially bottom line of the screen. And you can also compute, very easy to compute, that the relation between x and y is given by the plane curve y squared equals x cubed minus a squared x. So this too is a moduli problem, if you wish. Right-angled triangles with area A are parametrized by this curve. And a positive integer a is called a congruence number if it is the area of such a right-angled triangle. So from the above discussion, as I say in the slide, it's the area of such a triangle if the equation actually has a solution. It turns out that if there's one solution to that equation, there are infinitely many. And so if there's one right-angled triangle with area A, with rational sides, there are infinitely many. And I've now considered three types of curves. I call it the Pythagorean curve, the congruence number curve, and the initial curve we talked about, the Diophantus curve. These are members of the most basic trichotomy of algebraic curves, curves of genus 0, 1, and genus greater than 1. The Diophantus curve is of genus 2. The genus is didn't begin life as an arithmetic invariant. It began as a geometric invariant. It's the fundamental geometric numerical invariant of a smooth, complete algebraic curve or Riemann surface. And it depends only on the topological surface. And if it's of genus 0, it's topologically a two-dimensional sphere. If it's of genus 1, it's a torus. And if it's genus greater than 1, it's just a many-hole torus. But the arithmetic of these three types of curves differs substantially. For genus 0, any smooth projective curve of genus 0 over a field can be expressed as a conic. So you can use the sweeping method to produce rational points. That is to say, if that conic has a rational point, you get a one-to-one parameter family of rational points by a fan of lines through that given rational point. And it also has a very useful local to global property. The line at the bottom of the screen in red, it's locally solvable if and only if it's globally solvable. That is to say, it has a point, say, over the rationals Q if it has a real point and a p-adic point for all primes P. The question of whether something has a p-adic point, at least for any single p, is usually a very easy question. The question of whether something has a rational point can be as hard as you can imagine, harder than what Einstein suggested. Curves of genus 1 are of a totally different sort. A projective curve of genus 1, as I say here on the slide, that's known personally to many number theorists, is the displayed curve. It's very easy to remember 3, 4, 5 as the coefficients, and it's quite a famous curve. It was the first curve to show that the local to global property that genus 0 curves have is not shared by genus 1 curves. This one does not have the local to global property. And it has, let us say, it has, that curve has p-adic points for all p real points, but no rational point. But once a curve of genus 1 has a k-rational point, you can take that to the origin, and as in the figure shown at the beginning of this lecture, you get a group structure on it just by taking any 2 points, drawing the line between those 2 points, and working appropriately to find what you would call the sum of those 2 points. Such a curve is called an elliptic curve, that is to say a genus 1 curve with a rational point. And the set of those k-rational points is equipped with a group structure as hinted in the slide I just gave. And so you can think of it as it's commutative, a commutative algebraic group. The group of rational points is called the Mordell-Weil group of the elliptic curve over K, and Mordell proved over Q the theorem extended by André Weil to all abelian varieties over all number fields, that guarantees that these Mordell-Weil groups, they're abelian groups, are finitely generated. Now, the range of these questions of Mordell-Weil has been visited by mathematicians for, well, sort of close to a century now, and we're still only at the beginning of an unfolding story. Genus greater than 1 is completely different. That's where the Diophantus curve fits in. As I say here, although there's a well-known and dramatic prehistory of this subject dealing with specific curves, like the Fermat curve, I think it was only in the 1920s when people began to ask the general question, considering the arithmetic not of specific ones, but of all curves of genus greater than 1. And Mordell's conjecture is one of the principal sort of, let's say, pillars of the subject. Mordell conjectured in 1922 that curve over a number field of genus greater than 1 has only finitely many k-rational points. It was proved about a half a century later by Geert Foltings. So Diophantus' curve, which is of genus 2, we would know by Foltings, has only finitely many q-rational points. Finitely many points. Well, it was the mathematician Serge Lang's belief that, on the whole, arithmetic algebraic geometry, I should say, is really sort of, how to put it, it's really very much explained by specific structures, usually geometric structures that relate to it. And one way of asking one of his questions is the following: is it true that any variety over any number field possesses infinitely many k-rational points, if and only if there's a real geometric structure there? There's a connected algebraic group G over K possessing infinitely many k-rational points. and a non-constant mapping from G to that variety defined over K. So rational points are scarce. Now what I'm going to do is discuss, as I hinted at the very beginning of the lecture, what I'm going to do is discuss three essentially different arguments establishing finiteness of the set of rational points of a curve of genus greater than 1 defined over a number field K. And their methods at least originated by Faltings, Vojta, Paul Vojta, and a sort of an emerging, a more and more powerful approach, initially due to Chaboty, then Coleman, and then Mignon Kim. As I say, the last of these methods only work under further hypotheses. So it's not really a full, if you wish, proof, but it has sort of interesting features that make one often be able to actually find the actual rational points. Also, I say at the bottom of this screen, I'm not going to really give an exposition of any of these. I mean, that would be too technical. But I just want to invoke exactly as much of their nature as I need to appreciate how thoroughly incomparable they are. That is to say, incomparable ways of proving that a certain set is finite. So, Gert Faltings. Now, his method applies generally and was the first full proof of Bordel's conjecture. Vojta, his method also applies generally, and then there are elaborations and some simplifications by Faltings, Bombieri, and McQuillan. And with Chaboty, he began, I guess, he was working in the 30s and 40s, and his method only works on some restricted hypothesis that the genus of the curve is greater than the rank of the Mordell-Weil group over the Jacobian index. And it was sharpened later and led to a kind of semi-effective theorem under the same hypotheses by ideas of Robert Coleman. And more recently, as I say, has been made even more powerful by ideas of Mignon Kim. And he manages to deal with a range of examples that don't satisfy the restricted hypotheses required by Chaboty. Now, the Chaboty-Coleman-Kim method is currently being used and augmented and improved, and by many people who are finding rational points on some extremely challenging and important curves. And here's the list of people. Others include a number of my students in my topics course. And much more recently, there's a very intriguing extra here due to Brian Lawrence and Akshay Venkatesh. In their very recent work, we get a proof of Mordell's conjecture that it seems to have some of the flavor of Faltings' approach, but also has the spirit of Chaboty-Coleman-Kim. So as I hope, maybe this is the beginning of a way of unifying unifying surprisingly, seemingly incomparable methods. Now, we're talking about finiteness, so I should talk about various types of finiteness. When you claim that a set of rational points is finite, you could mean that you proved that there's a really explicit constructed upper bound for the heights of the rational points, or you might mean that there's an explicit constructed upper bound on the number of rational points, and they're quite different. if you've bounded the heights, it's really possible that you've set the stage for actually finding the full set of rational points. That is, if your bound isn't too high, you could systematically test by computer all the points of, just keep going, trying to see whether you get these rational points with rational numbers of heights less than your bound to see if they yield points on the curve. And also, your bound might also allow you to compute an a priori finite estimate on the amount of computer time it would take to resolve the issue. But the consequences of bounding the number of rational points is quite different. The best would be if your upper bound were the actual number of rational points, and then you could look and you might find them all. But that's rarely the case. But that's rarely the case. And you won't know before this event happens that it would happen, nor would you have any a priori time estimate for when such a thing might happen. In many setups, as I say here, where you have an upper bound for the number of rational points, that upper bound is far greater than the actual number of points. So even if you got all the rational points, you may never know it. And all the proofs that we know are really of the second type. They bound the number, but not the height of k rational points, leaving us with the fundamental question, is there actually an algorithm which has input, a curve of genus greater than 1 on a field, and the output, an upper bound for the heights of points? That's really an open question. Okay, how the theme of the beginning of this lecture is that there are incommensurable, if there are incommensurable methods of proving finiteness of something, why is the thing finite? So how different are the different proofs of finiteness of the number of rational points of curves of genus greater than 1? Is there some way of fitting these different approaches into one coherent picture? So let's go through them. The method of faultings gives you finiteness as a constant consequence of finiteness of quite a different species of mathematical object, namely isomorphism classes of abelian varieties with good reduction outside a finite set of primes and a bounded polarization degree. Well, I have some red lines there. I should comment on roses in the garden is less than flowers in the garden is less than infinity. Suppose you want to know how many roses there are in your garden, and all you can do is prove there's a finite number of flowers in your garden. Well, you now know there's a finite number of roses in the garden, but the bound that you have has nothing to do with the specific issue of how many roses are in your garden. It's similar here. You have a bound, a finite bound of some mathematical object which implies a finite bound of rational points on curves, but the implication is indirect, and you're bounding, in some sense, you might say a much deeper object, and so therefore you've got a stronger finiteness theorem, but the stronger finiteness theorem comes along with a weaker bound for the initial question. The method of Vojta is totally different. It's guided by analogies that relate finiteness of rational points to problems in very different arenas of mathematics. Hyperbolic geometry, approximation of algebraic numbers by rational numbers. His strategy takes off by banding together a large collection of rational points, sort of forcing them to give a point in a high power of the initial curve. That's I write here, for a large enough m where the pi's are rational points of x, and their heights have to be appropriately growing. I mean, in fact, humongously growing. And then you get a contradiction. Now, it's reminiscent of the shape of the proof of classical Roth's theorem. So what does Roth's theorem tell you? You have an algebraic irrationality, real, and you want to know best approximations. This is the most classical problem in, about numbers, about irrational numbers. And you want to judge the worth of an approximation of your irrational number alpha by a rational number p over q in terms of how close it is as an approximation relative to the denominator q. And you're not going to get it too close, says Roth. He says that there are only finitely many rational numbers p over q that approximate this irrationality as closely as 1 over q to the 2 plus any specific epsilon that you fixed. Now, his strategy is to suppose that there are infinitely many such good approximations and to combine enough of them to make one vector in a humongous Euclidean space just by putting them together as entries of a big vector. M has to be enormous, and since they're good approximations, what you've got is a pretty good approximation to the diagonal M tuple in the same Euclidean space. And then Roth gets a contradiction by just cleverly engineering polynomials in M variables that vanish to high degree on the diagonal irrationality, but don't vanish on that rational number v. So since a polynomial, it has coefficients in z, and since the vector is rational, the minute you know that it doesn't vanish, it follows that you've got a lower bound for it, lower bound in terms of the denominators of the situation. But since f was contrived to vanish on the irrational diagonal number, and since v approximates you get a contradiction. You get a polynomial with coefficient z that vanishes somewhere and just has a lower bound for its non-vanishing very close. That's quite different from Falting's proof. And the third incommensurate method of proving finiteness of rational points is by Chabot, Coleman, Kim. And here's a way of thinking about how that method offers finiteness of that number when it applies. It doesn't always apply. So imagine if for a given curve of genus greater than 1 over a number field, you had an algorithm that produces some non-trivial meromorphic function on the complex analytic Riemann surface attached to X, such that somehow by construction, that function vanishes on all k rational points of X. Well, since phi has only finitely many zeros, and very often this is a computable thing if you have a sort of an algorithmic expression for this meromorphic thing, your algorithm would have shown finiteness of rational points. And also, it does a bit more if it's really algorithmically explicit. The algorithm will exhibit any finite number of Taylor series coefficients at any of those points. And so therefore, you get much more information than just finiteness. You get an upper bound not only for the number, but on the possible locales of the rational points. But that's a whole fable. There is no known finiteness proof of rational curves, of rational points on a curve of genus greater than 1 that follows that scenario. But that's because I took the complex curve and viewed it as a Riemann surface. Things change if I replace the complex numbers by p-adic numbers. P-adic completions of the number field K, and you replace the requirement that alpha be meromorphic on the Riemann surface by the requirement that the function be the natural version of meromorphic, but even somewhat more local, be locally p-adic analytic on the p-adic analytic version of the curve. And it's good if that p-adic analytic function has actually a power series on every residual disk. But then the method of Chaboty only, of course, when it applies. And Coleman, Kim, and others have sort of made it apply in greater and greater generality, proves finiteness by offering such a function. And here's a cartoon that gives the barest hint of how the method of Chaboty and its recent extensions work. I don't know, can you see that? I hope so. You have what I'll call, it's a cartoon. You have some kind of what I'll call linear space. I'll say technically what it is, but it has a kind of linearity to it, a linear feel to it. And you have the curve embedded in this linear space. It's embedded analytically, possibly by logs or polylogs or something of that sort. And then you know that all the rational points of that curve lie on some proper linear subspace. You also know that the curve generates the big linear space. And so therefore, just by sort of the luck of the situation, you get that you have a finite intersection between the proper linear space and the curve, and therefore you get finiteness. Now, usually in applications, what they do is they find a function on the big linear space that vanishes precisely on the small linear space, and then they win. Completely different method than Vaulting's method or than Voigt's method. I should now go back to the Diophantus problem and so point out that this curve of Diophantus has its Jacobian has Mordell-Weil rank actually equal to the genus, so it's non-amenable to the straight classical method of Chaboty, but a mild extension of it can be applied and was successfully applied by Wetherell's thesis to find a single intersection point. Now, Diophantus curve is a curve of this very well-studied family of curves. It's a hyperelliptic curve. Definition, curves that are double covers of the projective line So of the form, for example, y squared equals f of x, where f of x is some polynomial but with no multiple roots. These are called hyperelliptic curves, and they're an intensely studied family of curves. And if the degree is large, if the degree of the polynomial is greater than or equal to 5, these curves are of genus bigger than 1. And I have a little red thing here saying, mention Drosophila, which reminds me that at least at, let's say a few decades ago, if you ask a biologist about the properties of animals or insects and so on, they would be very, very happy to talk about fruit flies and Drosophila because that's what they studied at that time, really intensely. It's similar to hyperelliptic curves. If you ask in number theory, hyperelliptic curves are the most, let's say, at the moment, the most intensely studied for the rational points. Studied in many ways, studied statistically, for example. If you fix the genus and you order the isomorphism classes of hyperelliptic curves in a reasonable way, in any reasonable way, really, you can ask statistical questions about the set of those curves. Now, if the degree is odd, the curve definitely has a q-rational point. It's the point at infinity, and it's a Weierstrass point, a very good base point for the curve. So you can ask, for example, is it true that with probability 1, that rational point is the only q-rational point of the curve? Now, Bjorn Poonen and Michael Stoll have shown that most of them have only the one rational point. And more specifically, if the genus is greater than 3, a positive proportion of them have only that point as their rational point. And this proportion tends to 1, actually, as the genus goes to infinity. And well, if you're interested in hyperelliptic curves with 1 rational point, what about hyperelliptic curves with 2 rational points? And Shankar and Wang show that at least if the genus is greater than or equal to 9, a positive proportion of hyperelliptic curves of genus G having 2 non-Weierstrass, that is, say, not fixed under the involution y goes to minus y, rational points, have exactly those 2 rational points, and that this proportion tends to 1 as the genus goes to infinity, and even more, how to put it, more generally, really, under the hypothesis that the hyperelliptic curve is locally solvable hyperelliptic curves very often have no rational points, not globally solvable, and that's a theorem of Bargalva, Gross, and Wang. Here's an atypical collection of hyperelliptic curves given all those theorems that I've just recited. You take the curve y squared equals, well, as displayed on the screen, where the AI, A1, A2, up to AD, are distinct rational numbers, and C is a non-zero rational number. And you want this curve to be smooth. And you discover that, of course, you can let x be equal to A1, and that means that whole expression at the on the right-hand side, except for the c squared has go to 0, is specialized to 0, and then you let y to be plus or minus c. And you do the same with x equals a2 up to x equals ad. And you get 2d, at least, rational points, the obvious ones, which is about 4 times the genus of that curve. It's atypical because you've got loads of rational points on this, and I've just recited the statistics of the hyperelliptic family having very few. Anyway, now you might ask, how many rational points does a general algebraic curve, no longer hyperelliptic, of genus greater than 1 have? And so one has that atypical collection with about 4G points. You might ask, can you beat that? That is, say, for any number field, K and epsilon, positive, can you find, for arbitrarily large genus, infinitely many curves defined over K of that genus G with more than, not 4G, but 4 plus epsilon G K rational points? I mean, it's a challenge. I think it's an interesting question to play with. And it is rather interesting that even after 17 centuries, we're still at the beginning of any full understanding of the nature of rational points on algebraic curves. And here's Einstein again, who seems to be in a happier mood about mathematics. Pure mathematics is, in its way, the poetry of logical ideas. One seeks the most general ideas of operation which will bring together in simple, logical, and unified form the largest possible circle of formal relationships. So, thanks for listening, and I hope we're having a nice discussion. What happens now?
Okay.
Yeah.
Yeah.
Okay.
Thank you very much. But so while they are setting up the microphone, well, I'll say a few words maybe. So I'm Michel Lapidus. I'm the AMS Associate Secretary for the Western section, and Georgia Benkar, my counterpart for the Central section, is here. As you know, this is only the second in history joint meeting between two sections of the AMS, as far as we know, and it's probably going to be the largest meeting of sectional meeting of the AMS. It's number 1147. Okay, I think we have microphone now. Well, I would like also to thank many people who have helped with the organization of the meeting, including the AMS staff, Melissa Colton here in the back, Gina Asfeld, and Penny Pina, who is the director of meetings, who is not here, but has been very helpful. And of course, the whole, the mathematics department at the University of Hawaii. Okay, so so there'll be a Q&A session that will last about 15-20 minutes, depending on how many questions there are. So please come at the front if you want to ask questions. Don't be shy.
I'm going to call out. Can you say something about Drosophila? That is, there's another proof of Falting's theorem.
Yeah, there's another proof of Falting's theorem. Yeah, that's true. That's true. Yeah. It's true. I would, if I had to put that into the mix, I would say that it is equally incomparable to any of the other proofs. That's absolutely right. And one could imagine trying to unify Drosophila with well, one can only imagine trying to unify. I can't. The other issue is where to place Lawrence and Venkatesh's proof in this context. I would have to say that it's somewhere between Faltings and Chabot-Kim, And it might allow one to imagine that there's almost, if not a continuum, at least some organization of, if we think of, if you want to put Rajavsky's proof in this picture, we have Faltings, Chabot-Kim, we have Vojta, and then Rajavsky. I would put Lawrence and Venkatesh's proof as diagonal in this in the quadrant built out of. But I don't know where to put Rajavsky's proof exactly.
Yes, please.
I'm sorry. Is it working? Do I need to turn it on? Thanks. I'm sorry if I missed this in your talk, but I was wondering which, if any, of the three methods gives the best or smallest
Bound?
effective explicit bounds on
I think it's. I think at the moment it is the Chabot-Kim method, in that. But of course, the drawback there is it's not general. But when it works, it actually produces real answers. One test issue at the moment is, if I can use a little bit of technical language, there are the curves that are called x0 p plus, p being a prime. So x0 p plus is a moduli curve, and it's a modular curve of some sort, and its points classify really beautiful objects. Its points classify elliptic curves that admit a p-isogeny rational, such that if you divide by the p-isogeny, you get another elliptic curve. Elliptic curves over a quadratic extension of the original field with a p-isogeny, such that if you divide by that p-isogeny, you get another elliptic curve, which is the conjugate curve under that quadratic, under the Galois conjugation of that quadratic field. They're very beautiful curves, and in some sense, they, elliptic curves, and in some sense, they mimic, in some of their arithmetic, what are called complex multiplication curves. That is to say, curves that admit more endomorphisms than multiplication by integers. And complex multiplication curves of the right sort will give rise to such curves. So, if P is large, but it doesn't have to be that large, these modular curves have a genus greater than 1, and so there will be only finitely many such points on any one of them, so only finitely many such beautiful examples. Some of those rational points, one of those rational points will be a cusp, so you can throw that out, and the other of those rational points will be the ones that we predict from the complex multiplication ones that, and then there are these unexpected sporadic ones. Now, none of the other methods could approach that. On the other hand, the Chabot-Kim method does, or at least has begun to, and people are slowly actually finding the answer to this question. I mean, the classifying these rational points, therefore classifying these elliptic curves that are sort of like complex multiplication curves. Now that is a slow process, but It's only Kim's method that seems to be able to do it. And every 3 weeks I get a message that, oh, x0 67 plus was just resolved. And the general conjecture would be if the prime p is large, there'll be no more sporadic points. So the sporadic ones are normally, the unexpected ones are sporadic in the sense that they'll only occur for a finite number of primes. And it'd be very nice to either know the answer completely or have some sense as to how you could possibly achieve this. At the moment you can't. I mean, you can do it. You can do it curve by curve, but you can't do it in some systematic way.
Thank you for a very interesting talk. I'm fascinated by this idea of a conversation over 17 centuries. Now, this occurs only in a few fields. Mathematics is one. I suppose Greek literature still speaks to us, and ideas of democracy from Greece still speak to us.
Right.
But if you look at something like chemistry, the ideas of earth, air, fire, and water being elements are totally wrong. Lavoisier overturned that.
Yep.
It speaks to us not at all. They're irrelevant.
Yep.
Physics was the same way. The idea that force and acceleration are related to each other rather than force and velocity. What is it about these fields? What is it about mathematics and perhaps literature and maybe democracy that the Greeks got right and they got it so wrong in everything else?
That's my question. I mean, it really is, it's shocking. And every once in a while, if anybody's read Dionyma of Aristotle, it's not bad. And the fact that it's not bad in the sense that you can, I mean, it's wrong, but the way of thinking about species, the way of thinking, it's really good. Now, the fact that it's a surprise that one can make a long conversation about biology between Aristotle and current zoologists, if you want, or naturalists, is a surprise. But in a way, the fact that we can have these conversations between Diophantus and Wetherell, it's wonderful, but it's not a surprise, which is interesting. I mean, so what is it about mathematics? That's a long conversation, by the way. That's a discussion. Yeah.
Other questions?
Hello. Hi. Just thinking of finiteness, I'm wondering why we should expect there also to be finitely many different types of torsion groups in
Of
elliptic
finitely
curves?
many what?
Of the different types of torsion parts in the groups of elliptic curves. I'm not sure if there are other proofs of this theorem, but is that something to be expected for some reason?
I hope I can understand.
Types of torsion groups?
Yeah, the torsion parts of the groups of
Finitely many
rational
parts
part
of torsion
points.
groups.
Torsion groups, where? In what context?
As I understand it, the groups of rational points on elliptic curves.
Oh,
there's a-
torsion on elliptic curves. Yeah.
Right.
Oh, yeah. Great, yeah. Right. That, of course, is also, in the end, a moduli problem that you have, you consider the moduli question of elliptic curves with a given subgroup or a point of a given order fixed out, and then you form the modular curve associated to that. That is, say, for example, the modular curve associated to elliptic curve plus a point of order 37. That's a moduli problem. How many elliptic curves are there with points of order 37? Well, you formulate this and you end up with a curve of high genus. So that curve has high genus. That means there are only finitely many. Of course, the game is, in that case, not just to say there are only finitely many. The game is to actually find them. And it's been known for 40 years, 30 years, that there are only finitely many types of torsion subgroups, rational over Q in elliptic curves, defined over Q. So, and that is one of the structural finiteness theorems. In fact, the finiteness theorem is more specific than that. I mean, I can say what it is, but that might be a little technical.
You mentioned how Manoa showed that the rational points on an elliptic curve form a finitely generated group. Would you say that modern advances in group theory have continued to inform the study of elliptic curves today?
That what?
Would you say that like modern advances in group theory have continued to inform the study of elliptic curves today?
Well, group theory has lots of forms, and one way of interpreting it is just saying that understanding how the Galois group operates on, for example, the groups of torsion points of elliptic curves. This is an issue, but by group theory, I think you mean you might mean non-commutative group theory of some sort, or.
Maybe you want to come here.
I suppose more in the context of like people who study groups specifically, not necessarily with reference to elliptic curves. Like.
Well, look, every advance in the issue, look, every advance in any field of mathematics, in particular, every advance in understanding groups, could be non-commutative groups, would have some reflection in issues as issues in the arithmetic of elliptic curves. For example, you might ask, you have a group, say the monster group, and now you might wonder, given the fact that you have an elliptic curve over Q, and you might have quite a number of Galois extensions of Q with Galois group, the monster group, how many of those have the property that the Mordell-Weil rank of that elliptic curve, when you extend the base from Q to that extension field, how often does that Mordell-Weil rank increase? And that's a serious question. It's an interesting question. It's, in fact, a very interesting question, not only for non-commutative groups, it's a very interesting question for cyclic groups of prime order. For example, there is a conjecture of Chantal, Fernley, and Kizilevsky, which says that if the prime is greater than or equal to 7, there are only finitely many cyclic extensions with Galois group, cyclic group of order that prime, where you get increased Mordell-Weil rank. So anything that you could anything that you could prove, for example, about the extension fields with Galois group, the monster group, would be very useful for understanding the subtleties of the arithmetic of elliptic curves. In fact, there was a lecture yesterday by Mike Sieve, which went largely in that direction, and sort of knowing very deep classification facts about finite simple groups that were given to him by the experts like Aschbacher, and he was able to prove something along the lines, I don't want to say technically what it was, but along the lines of what it means to rational points when you extend the curve by another curve whose Galois group is that non-commutative group. Anyway, Mike Zeev's lecture, I understand, is recorded, right?
It is.
You have the slides. And I think if I was looking for something that has lots to do with simple groups and specifically non-commutative simple groups and arithmetic, it would be go to Mike Zeev's lecture yesterday. Buy the slides, and Hector has the slides.
More questions? I have one. So
Yeah.
how close are we to solving this Serge-Lang's conjecture that you mentioned?
What?
Serge-Lang's
we're
conjecture.
nowhere.
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 Yeah.
No, that's a good question. There isn't a chance that any of the techniques that we know will do it.
Okay. Thank you. So maybe it's time to thank Professor Mazur.